Hi everyone, and welcome to this second part on the operational amplifier. In this video, we are going to analyze a few op-amp circuits that are very common and useful. Let us start with the non-inverting amplifier. As we showed in the first part, the op-amp here works in the linear regime because of the feedback between the output and the inverting input. We can therefore conclude that the potential at the inverting input is equal to Vin. Now, if the op-amp was not present, the resistors would form a voltage divider. The point is that the divided voltage is not affected when the middle point of the divider is connected to the inverting input of the op-amp, because the current through the input is zero. Thus, the input voltage is equal to the voltage produced by the divider. All that is left is to solve for the output voltage, which leads to our final result. The output voltage is equal to the input voltage multiplied by a constant. Let us analyze now the inverting amplifier. And here, this is the last time that I explicitly mentioned that the regime is linear, as it should be a reflex now. Once again, this implies that the potential at the inverting input is the same as at the non-inverting input, 0 in the present case. When this happens, we will say that the inverting input is virtually grounded. Also, remember that the current through the op-amp's inputs is 0. This implies that the current through resistor R1 must be the same as that through resistor R2. This implies the following equality. And finally, solving for the output voltage, we conclude that it is equal to a negative constant times the input voltage. Now, let us see the non-inverting summing amplifier. This circuit looks complicated, but it really is not. The truth is that op-amps make things simple, mainly because their input currents are zero. Here we can notice that the bottom part of the circuit is exactly the same as for the non-inverting amplifier. So we can recycle our previous result and write that the output voltage is equal to 1 plus Rf over Rg times the voltage on the non-inverting input. So we need to figure out what Vin plus is. Again, we can take advantage that the current in the non-inverting input is 0, so the current through the resistors R1, R2, R3 must add up to 0. This leads to the equation on the left, which we can solve for Vin plus, resulting in the equation on the right. So, all we have to do now is to substitute this expression in here, and the circuit is fully solved. So, we have the solution, which looks complicated. But now we can make a choice for the resistors in order to obtain what we want. Oh, by the way, what do we want? The name of the circuit should be self-explanatory. We want the output to be the sum of the inputs. We can achieve this by choosing R1 equals R2 equals R3 and RF equals 2RG. This result can be generalized to any number of inputs. The inverting summing amplifier is slightly simpler because it requires one resistor less. We start the analysis by noticing that the inverting input is virtually grounded. This makes it easy to write that the sum of the currents that enter into this virtual ground is 0. We obtain an expression that we can solve for Vout, leading to the general solution of the circuit. We can now make a suitable choice for the resistors in order to obtain what we want. We just choose all of them to be equal. As before, this result can easily be generalized to any number of inputs. Being able to add potentials it is natural to wonder whether we can subtract them. This is precisely what the difference amplifier can do. We use here the property that the potentials at the inverting and the non-inverting inputs are equal. The potential at the non-inverting input Vin plus is easily determined since the resistors R1 and Rg form a voltage divider. We can use a similar argument to determine the potential at the inverting input Vin minus. However, the voltage divider formed by R2 and Rf is not grounded, so the formula for it needs to be generalized. We can do this by writing that the current through R2 must be equal to the current through Rf. We can then solve for Vin minus. Writing the equality between Vin plus and Vn minus leads to this equation, which we can solve for Vout, giving the general solution of the circuit. In order to obtain what we want, all we have to do is to choose R2 equals Rf and R1 equals Rg. As the name of this circuit suggests, the op-amp is capable of outputting the derivative of an input signal. Noticing that the inverting input is virtually grounded, we can easily express the equality between the current through the capacitor and through the resistor, which in turn is easily solved for Vout. If we choose an RC constant of 1 second, then the output becomes equal to the negative of the input signal's derivative. If the minus sign poses any problem, we can always pass the output through an inverting amplifier to get rid of it. Having discussed about differentiating a signal, it is natural to wonder whether the reverse operation is possible. This is what this circuit does. The analysis is very similar to the previous circuit, only the resistor and the capacitor have been exchanged. As before, we start by writing the equality between the current through the resistor and the current through the capacitor, which we solve for Vout. If we choose an RC constant of 1 second, then the output becomes equal to the negative of the input signal's integral. As before, if the minus sign poses any problem, we can always pass the output through an inverting amplifier to get rid of it. This concludes this second part, but we are far from being done with op-amps. We will see some more circuits in part 3.